So in the last video, we found a solution for the time part of the heat equation, and I made a mistake in the sense that the alpha should be multiplied the spatial derivative and not the time derivative. But since this is a math video and not a physics one, it doesn't really matter because everything is the same. I mean, what matters is the process of solving the differential equation. If a constant is in the other side, it makes no difference. So I'm gonna leave it like that. But you should know that in the heat equation, the alpha multiplies the spatial part. Anyway, so now we can solve the spatial part because we know that C, I don't know what I was writing here. Because we know that C is equal to minus k squared. All right. So for example, we are going to do something similar to what we did here. We are going to have that 1 over x, the function x, capital X, is equal to it is equal to C, but we know that C is equal to minus k squared. All right. So we can multiply everything by x, kind of like what we did in here, and we are going to have just the double derivative with respect to x of capital X is equal to minus k squared times capital X. All right. So first things first, we cannot integrate here because there is no easy way to integrating double derivatives with double differentials. It's just I think it's theoretically possible, but there is a much simpler way to solve this, and it's just to think which functions do you know that have this property that when you take the double derivative you end up with a minus some constant times that same function. And what are those functions? Actually, I have to remember. Oh yeah, I remember. They are the trigonometric functions sine and cosine, right? So for both of them have this property. So I know I have that the double derivative with respect to x, and you should be able to prove this if you don't believe me, that minus a squared is equal to minus sine square of a. I'm gonna erase that. To be an eraser, yeah, whatever. All right, and this is also something very similar is true for cosine, that if you have the cosine of some a of x, it's just going to be equal to minus a times the cosine of a of x. Yeah, so we have two functions that satisfy this differential equation. So which one is it? Which one is the solution? Well, you have to remember a very important theorem about differential equations. I'm not going to prove it here, but if you need to if you need to refresh your memory on that proof, I'm going to put some links in the description to videos in Khan Academy in which they prove this theorem. But this theorem says that the sum of solutions for a differential equation, the sum of solutions of any amount of solutions actually, is a solution. And that the multiple of a solution is a solution. So for example, like this means that let's say that you found two solutions for a differential equation. You found C1 and C2. All right. This means that you could have some C3 PO that is equal to C1 plus C2, and this is also a solution. And you could have C4 that is also a solution, and that is equal to 2 times C1 minus 3/5 of C2. This is also a solution. And you can construct infinitely many solutions like this using different constants, using this. And you can, and why not? You can use C3 and you can use C4. I mean, I could use, say that C5 is equal to C4 minus 2 times C3. Also, it doesn't matter. You can go on and on and on, and all of these functions will satisfy whatever it was the differential equation you got these two one from. So, and the best thing is to use both of them, and you will see why in a moment. So we are going to use sine and cosine. So, here I have minus k squared. So here the k is going to have the function of the a here. So actually, the solution is to say that x is equal to a. No, not a. I have already used a here. And remember, kids, you should never recycle constants. It's the only thing that you should never recycle. There's too much confusion involved. So it's times b times the c, the sine of k of x, plus c. Actually, I'm going to swap the constants because I want the cosine to have that. Whatever, I'm going to continue like that. Times the cosine of k of x. All right. So this is the solution, and you can try it. You can take the double derivative of this, and you will see that it satisfies the differential equation. And actually, that's it. We now can say, for example, safely, that u, that was equal to x times t, is equal to the sine of k plus c times the cosine of k times x times 8 times e to the minus k squared plus t over alpha. All right, but this is not the whole story, because we know that u has to satisfy three conditions. For one, the temperature in the sides of the sword should always be the same. So at the beginning of the sword is 0, and at the tip of the sword is the same. What am I writing there? Yeah, we know that this is true. When x is equal to 0 and when x is equal to L, the function is just 0. All right. And we also know that for all space, at the beginning, the function was equal to x. All right. This was the temperature distribution on the sword when at the beginning. So first, let's try to use these conditions, because our solution has to satisfy these conditions, and these conditions are only concern x. So let's try to satisfy those conditions first. So the first condition that we are going to satisfy is that I'm running out of time. Then, well, that x is equal to 0. I'm gonna show you how to satisfy these conditions, and we're going to continue in the next video. So n x is equal to 0, this is the first condition. We are going to take only the spatial part, that is the only one that matters here, and we are going to have b times the sine of k times 0 plus c plus the cosine times the cosine of k times 0 is equal to 0. This whole thing is equal to 0 because the sine of 0 is 0. This thing is equal to 1 times c, so this is equal to c, and it's equal to c times 0. All right, so this means that, this is good, because this means that I don't need the whole solution. I just need a part of sine. And for x equals to L, I just have, well, I already know that I don't have to use the cosine part, so it's just b times the sine of k of L is equal to 0. So I divide both sides by b, and I end up I end up with sine of k of L is equal to 0. So I'm going to take the arc sine of both sides, and this cancels the sine over here, and I end up with k times L is equal to the arc sine of 0. And what is the arc sine of 0? Well, your calculator will tell you that it is 0, but I'll tell you that that's only half of the story, because what really happens is that sine is 0 for any whole number, like 1, 2, 3, 4, 5, 6, 7, 8, whatever, multiplied by p. All right? So we know that we can say that, hey, look, k is equal to n times pi over L. And this is important, but I'm going to explain this part in the next video. And in what remains in this video, I want to explain the following. Like, we knew that we could use as a solution either sine or cosine in the differential equation, but we decided to use both. And if we had decided to use sine, there would have been absolutely no problem. We would have gotten to the same condition. But if we had only used cosine, then we would be in trouble, because we would have found that c was equal to 0, and then we would have not find anything here because this was already 0. So this would have meant that the whole spatial part would be equal to 0, because if you only choose cosine and c is equal to 0, so you would end up with the whole spatial part being equal to 0, and you would end up with the whole solution being equal to 0. And it's not, and that means that everything remains constant. That, I mean, like, it is a solution, but it's a solution that tells you nothing, and that's not a very good solution. It's like if I tell you, well, I cannot come up with a good excuse, but it's like if I ask you not to lie and you decide not to say anything because you are not lying, and I didn't want that. I wanted you to tell me the truth, not to just remain silent. So if we had chosen cosine, it would have been like this. We would have gotten no information. We would have gotten not truth. We wouldn't have gotten any lies either. But I mean, you end up knowing nothing more than what you knew before. So when you are dealing with differential equations, you, more often than not, will have many possible solutions, like in this case, and you have to use all the solutions to find the real solution, the true solution, when you use the boundary conditions. Because if you only use one of them, you might find yourself with just the solution of x equals to 0, or you will find, or worst, you will get results that tell you nothing or that tell you lies, and we don't want that. So this is actually very important, and will come up later as we advance through the Fourier series. But I just want you to remind that when we are solving a differential equation, we are just not learning how to get the solution. No, you are never getting the solution. You are getting a solution, and more, you are getting how to make the solution. Yeah, you're not getting like every solution you find to a differential equation is one part of the true solution, and you have to use the boundary conditions to find the whole thing. All right, so if this doesn't make sense right now, if it's too confusing, don't worry, it will make sense later. This is it for now. Follow me in the next video, where we will and to use the, if I measure the time correctly, we will get the complete solution for this example.